All right, so today we're going to continue talking about our unit circle. We're going to define what a unit circle is and start talking about trig values and how to find trig functions for at least our special angles and our quadrantals, and a little bit about where that comes from. Okay, so quick reminder, sine, cosine, tangent, of course, and cosecant, secant, cotangent, the abbreviations and how we come up with those ratios. Sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent, cosecant hypotenuse over opposite, secant hypotenuse over adjacent, and cotangent adjacent over opposite. We remember all that, right? And we are going to talk about how to find all of those within a circle. Okay? So a unit circle, which, hang on a minute. Yeah, we'll actually define some more in just a second, okay? I want to talk a little bit more about how those trig ratios apply to what we've been doing from the last class, right? So we talked about these angles sitting in a circle, talked about these angles sitting in the coordinate plane. And so if we were to consider finding a point on the terminal side of an angle. Okay, so for example, we've got this angle here in standard position. Its terminal side is here, and we're going to consider some point here has coordinates x comma y. Okay? Now, one thing that when we talked about all of the things that we remember about a circle, one thing that didn't come up was the equation of a circle, right? Do we remember the equation of a circle? You'd have to remember that the center was given variables h and k. A point on the circle is always going to be x comma y. It's just a point. And so do you remember that the equation of a circle was x minus h squared plus y minus k squared equals r squared, right? That comes from a couple of different places. I mean, Pythagorean theorem, basically. If you were to go through and create a right triangle from that point. Distance formula is another way of deriving that equation. But if we look at the equation for this circle, h and k is the center, right? And so if we're talking about standard position for our angles, then the vertex is going to be at the center, and that should all be at the coordinate 0, 0. So 0, comma 0. That means h and k are both going to be 0. Well, that will simplify down into x minus 0 is 0, and then square that and you get x squared. X minus 0 is x. Square that, you get x squared. Y minus 0 is y. Square that, you get y squared. And so you end up with that equation there, which we will definitely come back to use a little bit later on. Okay, now, let's think a little bit about how we plot points and the fact that if we were to plot and draw the path of our plotting, we're going to get a right triangle, right? In other words, if a point is x comma y, then we're going to go over x, so this distance here is going to be x, and then we're going to go up y. This distance here is going to be y, and this is your radius r, okay? That's your Pythagorean theorem, x squared plus y squared equals r squared, which also gives you the equation of this circle, right? But it also gives us some direction on our trig values, right? Our angle is right here. So that's how we always measure the angle. The measure is there in the vertex. The angle is there at the measure is there at the vertex. All right? Now, if we were to use that as our angle measure, then we can write the ratios of our trig guys here. Right? Sine is opposite over hypotenuse. So the opposite is y, and the hypotenuse is r. And the distances that I've gotten down here, right, x and y, are just the same as the coordinates that were given, x comma y. Okay? Cosine from that theta is going to be the adjacent over the hypotenuse. Tangent is going to be opposite over adjacent. And then cosecant, just flip over sine. Secant, just flip over cosine. And tangent, cotangent, flip over tangent. So what does that mean? Well, if we're given a set of coordinates, something like maybe 2, 3, then we know that this distance is going to be 2, this is going to be 3. We can Pythagorean theorem to find the radius, and then we can write all of our trig values if we wanted to sketch the triangle. If not, we make the link between the point, the coordinate, x-coordinate here, and the radius here, right? It's just y over r for the sine, x over r for the cosine, so on and so forth. So there's a link between the coordinates and these trig values. So if we're given the coordinates for a point on the terminal side, no matter how big or small the circle is, we can come up with the sine, the trig values. So the trig values for whatever angle that is. It doesn't matter what angle that is either. Okay. So, for example, here, right, if we have some angle that's in standard position and a point on the terminal side is 5, 12, okay? Well, we can go through and all the stuff that we just went through, sketching the angle, wherever that is, and who knows where that is. Well, right 5 up 12 would put you in quadrant 1, so somewhere in here. So 5, 12, right? Now, if we were to take that point and plot it out, that would give us a distance of 5 down here and 12 up here. Now, to write all of our trig ratios, we have to have the radius. So Pythagorean theorem. 5 squared plus 12 squared equals r squared. 25 plus 144 equals r squared. 169 equals r squared. Square root both sides, and you get 13 for this hypotenuse, which is also a Pythagorean triple, so 5, 12, 13. Now, again, your angle is sitting here, so we can go through our sine of theta, cosine of theta, and tangent of theta, and it's asking for exact values, which means that we don't want to type this into our calculator, get a decimal and round it. We're just going to write the ratios. Sine of theta, opposite over hypotenuse, is 12 over 13. Cosine, 5 over 13. Tangent, 12 over 5. And then we can flip these over. 13 over 12 for cosecant. 13 over 5 for secant. And 5 over 12 for cotangent, right? But you don't even really need to sketch out the triangle, right? I mean, just look. In order to find the radius, all you do is square the x-coordinate, square the y-coordinate, and that becomes your Pythagorean theorem every time. This will happen every time. It doesn't matter where that point is that's on the terminal side. It doesn't matter what the terminal side is. Quadrant 1, quadrant 2, 3, or 4. It doesn't make any difference. Okay? Now, you see the special right triangles down there. We're going to bring those in starting now. Okay? Because we're going to introduce a unit circle. A unit circle is just a circle whose radius is 1. Always, always 1. The radius is always 1. And the center is always at the origin, just like all of our standard position angles. Okay? So this radius is 1. Okay? Now, if that's the case, then consider an angle that's at 45 degrees. Right? So this first one is meant to have a 45-degree angle. If that radius is 1, then we can find the other sides of this right triangle, just using our specials that we used all throughout the last unit, right? Remember that this is radical 2 side, this is one side, this is one side. So the two legs are going to be the same. Since we're going from the hypotenuse to a leg, we're going from a longer side to a shorter side, we've got to divide that 1 by radical 2. So this is going to be 1 over radical 2. But then we rationalize, and we get radical 2 over 2. Nice thing is, these are both the same. So since we're going over radical 2 over 2 and up radical 2 over 2, then we get to this point right here where the coordinates are radical 2 over 2, comma, radical 2 over 2. That's going to be the coordinates of our point on a terminal side of a 45-degree angle in the unit circle. And it comes from that relationship, the side relationships, right? This next guy is supposed to be a 30-degree angle. And if our hypotenuse is 1 here, we can find our other two sides using our relationship, right? This is 2 side, this is 1 side, this is radical 3 side. Nope, sorry, take that back. This is 1 side, this is radical 3 side. So to go from the hypotenuse to the short side, which is the way we want to go, we got to divide, right? We want to make that smaller. So we get 1/2 here, 1 over 2. And then from the short side to the long side, we want to make that bigger, so we multiply by radical 3, which gives us radical 3 over 2. Which means that the coordinates for our point here are, we go over radical 3 over 2 and up 1/2. And then this last guy is at a 60-degree angle. And so the same thought process ensues. The length of that hypotenuse is 1 because the radius is 1 in the unit circle. And so now we're looking at this, and this is going to be, this side right here is going to be on 1 side. This is our radical 3 side. This is our 2 side. So to go from the hypotenuse to the short leg, we've got to divide by 2. So we get 1/2. And then to go from the short leg to the long leg, we've got to multiply 1/2 by radical 3, or just get radical 3 over 2, which means that the coordinates of this point right here are going to be over 1/2 and up radical 3 over 2. So now we've established the coordinates for our 3 specials, 30, 45, and 60-degree angles in our unit circle. So let's apply that. Okay, I'm going to go all the way over to here, to our unit circle, right? And what we should have in here already. So 0-degree angle here, 0 pi, right? If this is a unit circle and the radius is 1, we should be able to come up with the coordinates for that point right there, right? If the radius is 1, then this point should just be 1, 0. Now, the next spoke on our unit circle is supposed to be for the 30-degree angle. Okay, from what you studied last time, in radians, 30 degrees is pi over 6. And from what we just talked about, if you were to go back through that right triangle where the radius is 1 and come up with your sides, we would realize that this coordinate is radical 3 over 2, and this is 1/2. But think about it like this. From that point, are we going farther in the x direction or in the y direction? Are we going more x or more y? And the answer to that is we're going more x. So x has to be bigger than y. And x, the numerator, is radical 3. Well, we have a choice, right? It's either radical 3 or 1 with our 30, 60, 90. That's our relationships, 1, 2, and radical 3. So hopefully it makes sense that the x coordinate is radical 3 over 2 and the y coordinate is 1/2. We're going to kind of keep using that thought process. We've already come up with these coordinates. Let's just write them in. So 45 degrees here, and as a radians, that'd be pi over 4. And those coordinates were radical 2 over 2, radical 2 over 2. In this 60-degree angle, pi over 3. And those coordinates were 1/2 and radical 3 over 2. And so I guess what I was trying to get at before is that the square root of 3 is bigger than 1. And so when we want to talk about, so I want to use the fact that radical 3 is bigger than 1. So we start talking about, are we going farther in the x direction or farther in the y direction for our coordinates? Those are the options we're going to start thinking about, right? Radical 3 is bigger than 1. So when we go back to the 30-degree angle and we see that we're going farther to the right than we are up, we're going more x than y, then the x coordinate should be larger. Since radical 3 is bigger than 1, radical 3 over 2 comma 1/2 becomes our coordinates, right? And then we go around filling this in. This is 90 degrees, which gets us pi over 2. And then we're going to go 0 in the x direction and 1 in the y because, again, the radius is 1. All right? Now, the rest of these, we haven't filled in the rest of the spokes, right? We did do the quadrantals. This guy's 180 degrees. This is pi. The coordinates for that point are going to be -1 comma 0. Down here it's 270 degrees, or 3 pi over 2. Those coordinates are going to be 0 comma -1. Okay, because again the radius is 1 here. Now, every spoke should correspond to spokes like they did in the first quadrant, right? And there's two ways to look at this. The way we see this is, if I'm going to go from here to here, then I'm going to go into 90 degrees plus another 30. So this is going to be 120. Okay? But it's 90 plus 30. So we're talking about a 30, 60, 90 triangle again. So it's going to correspond to one of our 30 or 60 angle guys in the first quadrant and how the coordinates will shake out there. So 120 as radians, right, is going to end up being 2 pi over 3. Now, look at where that point is. Is it more in the x direction or more in the y direction? And hopefully you would agree that's more in the y direction. So our y coordinate is going to be bigger than our x coordinate. So it's going to give us a set of coordinates of 1/2 comma radical 3 over 2. But also look at where the point is. The point is left and then up. Left for the x direction is negative. So this should be -1/2 radical 3 over 2. Okay, the next spoke would be 90 plus 45 degrees, or in other words, 135. Okay, which would correspond to a radians of 3 pi over 4. Now, if you're at a 45 degree angle spoke, which is what the 135 degree angle spoke is, then you're not going any more in the x direction than you are in the y direction. You're going the same. That's because 45 degrees is right in the middle of 90 and 0. 135 degrees is right in the middle of 180 and 90. So that means that both of our coordinates are going to be the same, radical 2 over 2, radical 2 over 2. And again, it comes from that 45, 45, 90 triangle. But again, we're going in the negative x direction, so x is negative. Next angle is 90 plus 160, so it's 150 degrees. In terms of radians, it's 5 pi over 6. We're going farther in the x direction, so now x should be larger, radical 3 over 2.5, and then we're going left, so that x has to be negative, and that's how we're going to fill this in. There is a pattern here too, right? Yes, more x or more y helps, but also look at the radians. The radians will help, right? All of your spokes that correspond to having a denominator of 3 are going to be the same coordinates, 1/2 and radical 3 over 2. You just got to figure out the sign. Every set of spokes that correspond to a radians measure of a denominator of 4 are going to be radical 2 over 2, and every spoke that has a radian denominator of 6 is going to have the same coordinates, radical 3 over 2, comma, a half. So there are some patterns to be had here to help you learn this. All right, so let's keep going around here. The next spoke is going to go be 30 degrees after the 180, so 210, right? Now that spoke should correspond to a denominator of 6, right? So this is going to be 7 pi over 6, which means since it's over 6, we're going to have radical 3 over 2 and a half. Now, signs, we're going left and down, so both of these are going to be negative. Next one is 180 plus 45, or 225. That's going to give us a denominator of 4. And so we're going to have 5 pi over 4. And that's going to give us radical 2 over 2, radical 2 over 2. Since we're left and down, these are both going to be negative. The next one is 240, which is going to give us a denominator of 3. Which, sorry, got to do some quick math here. Divide by 180. Uh, 4 pi over 3, right? It's going to be 4 pi over 3, which should get us, let's see, less x, more y. Make both of these negative. Then we've got our other guys over here. So 270 plus 30 is 300. That in radians is going to be, what, 5? No. Sorry, hang on. 5 pi over 3. Okay, which should get us to the coordinates of 1/2 radical 3 over 2, where more y and less x. Signs here, we went right and down, so now your negative is on your y coordinate. 315, right, is going to give us 7 pi over 4, which is radical 2 over 2, radical 2 over 2, the y is negative. And then last, 330, which is going to get us 11 pi over 6, which will put us at radical 3 over 2, 1/2, with the 1/2 being negative. Okay? So there's your unit circle. We can add 360 here and 2 pi here, and that's what you have to know. Okay? And there are ways to think through this. Okay? I'm going to stop here and pick up the rest of the video in just a little bit. It'll probably be in a second video, so look for that.